Let's start with a brief recap on randomized planning. We have seen that grid-based planning algorithms can be highly efficient. For example, when using A*, you can move pretty straightforward to the goal, but you still see that there's a lot of points explored in the space that are not actually helpful when you think about the fact that the goal is over here, and we yet have to explore all of these areas and all these points that are these individual grid cells. So we instead introduced a different approach to sample the space, and this is an important distinction because the RRT planner is mostly a sampling algorithm which samples a subset of the space. So instead of putting a dot at every grid cell, we come up with a way to create a much sparser sampling, and here we sample in different directions, and then once we find the goal, we actually do use A*, which is the same algorithm that you see here, to find the shortest path on the resulting path here. And as you can see, you now sample much less points, so there's much less computations you have to do, but in turn you don't get an optimal path. This is a path that could benefit from some straightening and other optimizations. In RRT, the sampling is doing the collision checking as well. So once you found 2 points that you would like to connect to the graph, you will need to look at all of the in-between points as well. You can see this very nicely here, where I actually physically, if you want, move the robot between 2 points before actually jotting down an edge as suitable. And if the robot runs into something, I put down a red edge because it didn't work to move forward that way. The state-of-the-art implementations of collision checking and robotics planning indeed use physics engines like Open Dynamics Engine. This is also how Webots is programmed, the tool we are using throughout this course, or the Bullet physics library. And the side effect of this is that you can actually really simulate arbitrary kinematics and dynamics even if you don't understand them yourself. For example, I've done this and put in a 6DOF KUKA arm as well as with some obstacles. And now all I have to do is I have to tell the simulator that I want to change the joint angles. Then I can not only see where this robot kinematics would move, I don't have to compute that myself, but I can also see whether it would collide with an object in the environment or not. And as you can see, this computation is not straightforward because it happens in full 3D space. Now in practice, this actually doesn't work so well. Here you see I try to move the robot to the yellow point, and as you can see, it hasn't found it yet. And what you of course would want to do is you would want to do some biased exploration that you've seen in RRT and move the robot arm toward that yellow dot every now and then. In order to do this, you of course do need the inverse kinematics. So you need to have some equations that tell you the joint angles that would correspond to the actual position. But that still means you can save a lot of effort in implementing this using a physics engine for the collision avoidance. What you also would want to do is, instead of making these large jumps in joint space or small jumps in joint space, which might be large jumps in Cartesian space, you actually would want to compute small incremental movements in Cartesian space, like this arrow I show here. And for that, you would use the inverse differential kinematics. Now, the good news is that these libraries usually provide you with these kind of solutions. So as soon as you define the geometry, you will get equations for the inverse differential kinematics, and you can then very easily implement a planner. For example, using a car, let it drive at 50 miles an hour and say, what would happen if I turn the steering wheel by 2 degrees? What would happen if I would brake? And you would get a realistic or quite realistic trajectory that you can use to build your tree. All right, now to the new topic, behavior trees. We have seen state machines in the past. The idea was that I have a finite set of states and I have an input alphabet that allow me to decide whether I want to move from one state to another. For example, I do follow the light until I hit an obstacle or detect an obstacle, or I am actually under the light, in which case I stop. And you have seen that this gets pretty limited pretty quickly. For example, if you want to implement something like going back and forth between an obstacle for, let's say, 3 times, then you would drive, do the first hit of the obstacle, do a U-turn, drive back, and go back and forth until you did the nth encounter, which you then lead to drive and finally stop. Now, as you see, the state expands pretty quickly with other variables like a counter, and for that we introduced the idea of having an extended finite state machine where you not only have an input alphabet to trigger the state transition, but you also have an action that follows every state transition, and in this case I use this slash symbol to delineate this. So there's no guard condition when you start, but then there's an action. I do set the count to be 0, and now whenever I do or complete a U-turn, I also increase the counter by 1, and then I can use this counter variable in my guard condition and say, if I hit an obstacle and the counter is n, that means I have made n U-turns, then I do stop. Now, this is also not that great, because you will find out that as you run your robot in the real world, the more you interact with it, you will find that you will want additional state transitions. Now, in the extreme case, you have one state transition from every node to every other node, as you realize that, for example, following a wall might directly lead to be under the light, and avoiding the obstacle again would actually drive you away from the light. So you will then realize, oh, I have to add this transition, you add this code, another if statement, and so it goes, and it becomes more and more complicated and becomes quickly unmanageable. Now, this is also the case when you want to add a state, and in this case I made up an example where I would say that after avoiding an obstacle, the robot might want to reorient, which is standing still and turning on the spot until it sees the light straight out ahead, and then go into the follow light mode. Same thing, as soon as you do that, you will realize that there might be other ways of, or other previous states that will require you to go into reorient, or you actually would want to go from reorient into directly stopping or whatever. So the idea I want to convey here is that adding a state really leads to a combinatorial explosion with many new potential transitions, and you are kept pretty busy with these kind of state machines. Now, robotics is not the only use case of state machines. There's a very big industry at 2022. This was a $217 billion industry, the video game industry. This is 3 times as big as the entire robotics industry. And here I'd like to point out that this is really just software, while the robotics industry is mostly hardware. Now, if you consider how small the robotics software industry is, you will see that a very much bigger, 10 times, 20 times as big industry is figuring these things out much faster. And since 2014, one of the main game engines, the Unreal Engine, has stopped using finite state machines and introduced behavior trees. So this is Unreal Engine 5, which is the current version, and the way this works is you have some kind of simulation view of your characters, and you can drag and drop what looks like state machines but is actually behavior trees. Here I have a close-up, and the idea is that if the agent has line of sight with you, the player, then it's gonna start chasing you down. How does it do that? It turns itself toward you, and then it starts chasing you and ending up moving toward you. If it doesn't have line of sight instead, then it actually goes into a patrol mode where it picks a random point, moves to that random point, waits there for a couple of seconds, hoping to run into you, in which case it then would start the chasing behavior. Now, these behaviors are, of course, as you know, for everyone who has played a computer game, much more complicated and are really intriguing for many years now, the AI in games has come pretty close to what humans can do. And so this is something that is unlocked with behavior trees. Now, what are behavior trees? Behavior trees are a software engineering tool. They're not really a formal method of any kind, and what they do is they provide you with additional abstractions. So instead of just having those states that you know from the finite state machines, you have additional graphical symbols that help you structure your behaviors. And then they actually come with a reduction. These states that can have all sorts of outcomes are reduced to simple behaviors that can either succeed or fail. Now, this helps you tremendously in putting them together into more complicated ones, because you can really encapsulate your behaviors and say this either works or it doesn't work. There's nothing in between, like sensor values being lower or larger than a certain value or something like this. It either has to fail or succeed. Now let's consider an example. I have a finite state machine here for peg and hole, and this is a square peg and that has to go into a square hole. If I want to do this, I have to move the peg over the hole, and then I have to rotate the peg so that the square peg is aligned with the square hole. And once I've done that, I can move the peg down until contact is made. Now, in a behavior tree, I will have very much the same code, and I have these leaves, as it's called in behavior trees, which actually implement the behaviors. Move peg over the hole, then I have this rotation step, and then I have some code to move the peg down. But now they are grouped into what is called a sequence node, and the sequence node only has execution behavior, so you usually don't write any code in those, but you choose them, and what they do is they will execute these children from left to right until the first one fails. If any of these fails, the sequence node will fail. If all of them completely run and finish, the sequence node will finish. Now, this is the most basic structure that you can have in a behavior tree. Now, I claim that the finite state machine does exactly the same thing. That's not true. If you actually want to implement this behavior in a finite state machine, you have to put in a lot more if statements. In this case, whenever I can fail in any of these leaves, this hasn't been the case before. Here the assumption was that these behaviors will always complete, so there's no other way than moving forward, or you get stuck forever in this. Now, in this case, I actually now have the opportunity to fail and bail out of that state, and I introduce two new states, which are the failure and the success state, and I can end up in the success state if all of them are completing successfully, or I can end up in failure if one of them actually does fail. So you see already here how a lot more transitions are implicitly covered in the behavior trees than are in the finite state machines, and how this forces you to actually think about failure behavior much earlier than you would do than if you develop a finite state machine. The second structure in the behavior tree is the selector node. This is using usually a question mark or something like this instead of the arrow. And what this does is it also executes all its children from left to right, but it actually goes on until the first one succeeds. In this case, it will run a leaf which is called sense if the peg is already in gripper. And if that fails, and only then, it will actually go and get the peg, which is a sequence node, which first locates the peg, then if that is successful, opens the gripper, moves the gripper to the peg, closes the gripper, and now I can assume that I have the square peg in my hand. So if I call this whole selector node again, it will sense that the peg is already in the gripper, this will succeed, and this will succeed. Now, what this actually does is it is essentially a priority selector which tries out different things with decreasing priority. So the first thing that it tries is what you see at the left. If that doesn't work, it tries the second child. If that doesn't work, it tries the third child, and so on. In this example, I only show 2 activities. Now let's compare this side by side. I have to the left the behavior trees that we just learned, the selector node to the bottom and the sequence node to the top. I have the finished state machines to the right, and again I have a lot of other states, other transitions that are implicit in the behavior tree. So in this case I can succeed right away if my peg is already in my gripper, and only if I fail then I execute that sequence that then needs to succeed, so that I end up in success, or I can bail to failure. Now again, you would never program the majority of these possible failure modes when you write a finished state machine in the first place. Why would you? Instead you would run into those only as you start deploying your algorithm and testing it. So here behavior trees help you to think about your problem in the right way. Now when you add a state, doing this in a behavior tree will require you to not only program these new states, but actually also change the previous state. So in this case, move peg over the hole has been wired to lead to rotate peg. I have to go inside that code, maybe somebody else has written it, and change where the next state is, and in this case I want to test the vertical alignment. Now when I want to do the same with the behavior tree, all I have to do is I have to insert a child in this sequence, and it will automatically take care of executing the necessary things. In this case I will test the vertical alignment. If that is already there, then it succeeds and I go on in my sequence, and otherwise it will run this vertically alignment step. So you can see this here. I can skip this step or not. Now this directly leads us to another advantage, which is the composability. You might now want to compose your pecking and insertion behaviors into a peg and hold sequence. The peg and hold sequence will first check whether the peg is already in my hand, and then go right away and insert it. Otherwise it will execute the sequence to obtain it. And you see that now we already have a very complicated state machine that is not straightforward to read. I really have to parse, where are these errors going, what do they say, what do they do. And imagine now I not only would have success and failure, but complicated alphabets or larger alphabets, and have to think about what does it really mean. Location is within a certain circle or radius, or in this case, in order to know if I already have the peg, or I have to measure the gripper width, things like this. These are now encoded in the leaves, and I can focus on simple success and failure and pass my tree by looking at the top node and then going from the left to the right. Alright, so far every leaf is executed until it completes, and in this case some things might go very quickly. Let's say like in 100 milliseconds you know whether you have your peg, and others might take very long. For example, moving the gripper to the peg might take 6 seconds. So the behavior tree is essentially stuck in this leaf until the movement has succeeded. This is pretty bulky. It doesn't let you do anything concurrent, and might lead to other problems. So what you would usually do is you would introduce some kind of real-time execution model to your behavior trees, and this introduces one new state which is called running. So before we had the states could be success or failure. Now there's a third one which is running, and while I move the gripper to the peg, the state returns running until it succeeds when it issues succeed. Now in behavior trees, there's a concept called a tick. The tick could be like 32 milliseconds, for example, like in Weebot's robot step. And whenever I call tick, I go to my behavior tree, I go to the current node, I advance or send commands to my robot, I advance time by 32 milliseconds, and then I either return running, failure, or success. Now with this, I can also parallelize my BTs. I can have multiple BTs that run at the same time, and I maintain different pointers of where I am at, and whenever I call a tick, these nodes execute a little bit of code and then wait. This is also helpful, of course, if I want to implement real-time reactive behaviors, which we will see later. Now, there are a couple more things to behavior trees that you will need. The first one is the parallel node. I have this here. It's a node which has two arrows in this case. And what it does, it executes all of its children at the same time, and it succeeds if all of them succeed. There are, of course, many options in different libraries on how this is actually implemented, so you have to read up on this, but it's the general idea. And here what you could do is you could have a behavior that constantly scans the scene and understands where all of the items are in the environment, and then there's another sequence that implements the peg and hold assembly. Now, another important concept in behavior trees is the so-called decorator. There are many possible decorators. Here I have one which is the repeat decorator, and what the repeat decorator does is it just keeps repeating its children forever. Now there are of course variations of this. You might have a loop decorator that does a certain behavior a certain finite number of times, but you also have decorators that would turn a success into a failure or turn a running into a success, which then allows you to use somebody else's behavior that has a certain output and actually invert it so that you can use it in a selector on a sequence node and get certain things done that you want to get done. To really understand this, it's best to implement a behavior tree yourself, and you will see that you will want these kind of things every now and then. Now finally, there's a concept called blackboards that most behavior trees implement, and in this case you would want to use the blackboard to write the location of the hole and the peg that the scene scanning behavior has found, and then you can use those variables in your peg and hole assembly. So you can of course use a global variable for this, which is not very elegant, or some other inter-process communication. Now in practice, most behavior tree libraries do come with this, and now we can go back and look at the Unreal Engine, and in this case you will see that the first node here is actually a selector. It checks whether you have line of sight. If this fails, it will go and execute the patrol sequence. Otherwise it will go and chase the player and run the sequence down below here. And now it says rotate to face BB entry, and BB is the blackboard that we've been just talking about. And this blackboard is populated in some other behavior tree that is not shown here, where probably down here in the patrolling actually, where when you see the adversary or the player in this case, you update the blackboard, and then the other agents can use that and run toward it. Alright, so this course has a final project, and in that final project you will want to create robust BTs to implement some basic behaviors like navigating from A to B, orienting with a target and grasping it, stowing the arm when you hold an object in your hand, and then finally placing the object somewhere else in the environment. And the idea here is to really encapsulate those behaviors, use the BT framework to implement them in a robust way, and then compose a final solution that is actually quite complex behavior and would be very, very difficult to implement using a finite state machine. Now there are two ways you can do this in this course. And the first one is you can build your own classes, and we will have a lab where we talk about how to implement typical nodes like selectors and sequences, and here you can already see how the data structure is working. These selectors and sequences are usually classes that keep lists of their children. In this case, the selector has the list of sensitive peg already in gripper, and then it has a sequence called get peg, which then locates the peg, opens the gripper, moves gripper to peg, and then closes the gripper around the peg. And this whole selector is creating something called pig square peg. The content of these classes is pretty simple. You essentially loop through your lists and then call these elements until all of them succeed, or the first one succeeds depending on what you have. But you can also use a behavior tree library like III.3, which not only implements these basic classes, but also a lot of interesting variations that might be useful in one or the other use case, as well as visualization tools like you can see here, where it looks at the class structure that you just created and creates a pi.dot tree view of it. So this is of course very helpful to debug the things that you have actually implemented and also see how things are executed step by step, and many more features. All right, I'd like to do an exercise with you, and that is to create a behavior tree for the light following behavior that is robust against U obstacle. So what you have to get is you have to create a sequence or a selector, as I suggest here, which is called move to light, and which succeeds once you are under the light and otherwise. So here is how this looks like. You actually would want to implement a priority selector that tries different actions from the left to the right. The first action is to check, am I under the light? Yes or no. If I succeed, I'm done. If I fail, then I want to follow the light. If that fails for some reason, I want to avoid the obstacle. And if that fails, because let's say I'm in a U obstacle, I want to follow the wall. Now, of course, you need to repeat this, and you will need to repeat this until this whole thing succeeds, which is a variant of that decorator if you want. And now you follow the wall a little bit. You again check, am I under the light? No, then I want to follow it. I want to avoid obstacles again, and so on. Now you already see that this is actually not the whole solution, but you would need to first put a lot of intelligent behaviors into those leaves. For example, how long do I follow the wall until I call it a success or a failure? And here I allude to this idea that once the light increases, I am now moving again toward the goal, and this is when I want to stop my light following behavior. But it also will depend on the timing. How many seconds do I give each of these behaviors until I know that, for instance, the avoid obstacle has failed? So in practice, behavior trees are not used for low-level tight reactive control like this. Instead, you tick these behavior nodes in the order of seconds, and you use them for higher level planning. This doesn't mean you cannot do what is shown here, and in that case you would probably want to pace those behaviors at a length of 1 second or 2 seconds or something like this, and implement robust behaviors that really detect whether the obstacle avoidance has failed in the time that is allotted by your tick. For composability, I'd like to show you a video from Picnic Robotics here in Boulder, where they use MoveIt to not only implement behavior trees, which you see here to the right, but also use natural language to automatically generate the behavior trees. And now that we use success and failure as the only possible states in our behavior trees, composing things becomes very easy and robust. All right, in summary, behavior trees are a class of abstractions that facilitate the definition of complex behaviors. They are not a formal mechanism, and there are many libraries and opinions on how to implement those. What all of these have in common is the idea of having sequences, selectors, and parallel nodes, which we talked about today, there are many possible ways of extending this framework, all with advantages and drawbacks, because as soon as you add to this, it becomes harder to understand, again, harder to debug, and so on. So what everyone agrees on is keep that set rather simple. Now, finally, the most important point is it is really the reduction to success, failure, and running that will allow you to unit test your behaviors and create robust implementations that you can then give to other people and put together in a complex manner.